Section 4, we're going to get into atomic number and atomic mass, or sometimes just called the mass number. And these are the numbers that pretty much any periodic table you have will have at least 2 numbers there in them. And so we're going to explain what those are. First off, the atomic number is a whole number. It's the same for all atoms of that element, so each element has its own atomic number, and it is equal to the number of protons inside the atom, or inside the nucleus, of course, because that's where they actually are. And usually, I will say it appears above the symbol. I have seen periodic tables without. I've also seen plenty of periodic tables with lots of extra data there, periodic tables with no data there, just names and or symbols, but it is a whole number that tells you the number of protons. I'll also add on there that it usually also tells the number of electrons, though the number of electrons can change. And because the number of electrons can change, it always tells you the number of protons. It only tells you the number of electrons if it's a neutral atom, not one that has become a charged atom, what we call an ion. Again, we'll get to that later on. So here are some examples. You can take a moment and read those. And here they're just stating again that the atomic number is equal to the number of protons. So fluorine, if you go look it up on the periodic table, it has an atomic number of 9. So 9 protons. Potassium has an atomic number of 19. Barium has an atomic number of 56. I'll leave it as a challenge to you to go look up the symbols for each of these. For example, that one's chlorine, and you could go through and use the number of protons to tell you the atomic number, and then look up what the element name or symbol is. So again, atoms are neutral, which means they have a charge of 0. And since they have a charge of 0, then we have to have an equal number of positively charged pieces and negatively charged pieces. Now that's an equal number. If we go for the actual sign of the charge, they're going to be opposite signs. So one will be positive and one will be a negative. So for example, when we have on calcium 20 positives, and we have 20 negatives, then together those two combine to give us a total of 0 for an atom. Again, atoms can change the number of electrons. Turns out calcium tends to prefer to lose 2. We'll get into that later on. At that point, we call it an ion instead of an atom, and it will have a charge, and the protons and the electrons are no longer equal. So here we have our different elements. I'm going to go ahead and say, you know what, let's practice name. That's sodium, zinc, and sulfur. I'll point out that it is a UR, not an ER, and the British way of spelling it is actually a PH. There's still no E there, and PH instead of the F, of course. anyway, for this then, we're asked atomic number of protons and electrons. Well, atomic number tells you the number of protons. If it's a neutral atom, then, or a element, then we're looking at a equal number of protons and electrons as well. So sodium is 11 all the way across, zinc is 30 all the way across, and sulfur is 16 all the way across. The mass tells us the mass of the atom. If you want to be picky, it then kind of tells us the mass of the nucleus. Electrons do have a little bit of weight. It's so tiny that it's pretty much negligible. And so then we could say that the mass number is equal to the number of protons plus the number of neutrons, which are the particles in the nucleus. I will point out that if we have lots of electrons, something like the element fermium. Fermium has an atomic number of 100. That means it has 100 protons, it has 100 electrons, and it turns out that there's a pattern that in the late periodic table after calcium, your number of neutrons is about 1.5 times your number of electrons. So it has about 150 neutrons in there. That gives the nucleus having a mass of about 250 total. Those electrons, since they weigh, it was the 0.0005, I think they add a whole 0.05 to this, if I wrote the correct number of zeros there. And so I like to think of money a lot of times when I'm doing calculations, as I think I've mentioned before, but if this is $250, the electrons give us a whole extra nickel. Well, if I have $250, I don't care about that nickel. It's negligible, and so we get to essentially ignore that mass. Now, I will point out here, they're being a little picky with how they define this, but they are technically correct here, that it does not appear on the periodic table because it applies to only individual atoms. Now, you'll look at it and say, wait a second, it's close. And you're correct, it's close, but it's not exactly, and we're going to get into here why they're not exactly. The mass number is equal to the number of protons plus the number of neutrons. We can look up number of protons in the periodic table. We can roughly look up the mass on the periodic table. The neutrons we can't. The neutrons end up being a calculation then. So we do a little bit of algebra there. We move the number of protons to the other side, and we can do mass number minus number of protons is equal to number of neutrons. Well, protons can also be worded atomic number. And so you'll notice then that mass number minus atomic number gives us the number of neutrons. The nice thing is on the periodic table, if you're looking at the mass number there, mass minus number of protons gives you number of neutrons. It's always big number minus smaller number gives you neutrons. Again, to be picky here real quick, hydrogen has a mass of 1, atomic number of 1, so it ends up with 0 neutrons. Other than that one example, mass number is always bigger than atomic number. Plus, if you think about it, it doesn't make sense to have negative neutrons inside of an atom. What would an atom be that is missing neutrons? So this table here just kind of organizes some examples and has all the information you could want. Again, the mass numbers here are going to be similar to what's on the periodic table. They're not exactly. We'll get into it soon here. But I do want to point out that there are occasions where the number of protons equals the number of neutrons. It does happen on occasion. However, it never happens again until after atomic number 20, calcium. It only happens for half the elements before that. Your odd numbered ones for protons tend to be ones that don't match, and it never happens again after calcium. Always after that point, there's more neutrons than protons, and it's about that 1 to 1.5 or a 2 to 3 ratio, as I mentioned earlier. But mass minus number of protons or minus atomic number equals number of neutrons. And so you can see that calculation was done here for each of these to give us those. And then the atomic number tells us the number of protons, and it also tells us the normal number of electrons, though those can change. Here it just kind of restates those things, so there you have it if you want. There's a typo there because it's missing a space, so fix that, but I'm moving on. So an atom of lead has a mass number of 207. How many protons? Well, we just go on the periodic table, look it up. It turns out it has 82 protons. How many neutrons are in the nucleus? Well, that's 207 minus 82. 82 from the atomic number. 207 is the mass number that was given to us, and that means there's 125 neutrons, and electrons would be 82 electrons. And then just to emphasize here, these are in the nucleus, and these are orbiting in the atom. Atom of zinc has a mass number of 65. How many protons are there? It is 30. That's just its atomic number. How many neutrons? That is 65 minus 30, and that gives you 35. And what is the mass number of zinc if it has 37 neutrons? So we have a different version of zinc here. Both do exist, it turns out. And so to figure out the mass number, we'd add number of protons plus the number of neutrons to give us 67, so that one there. Atom has 14 protons, so its atomic number would be 14, and 20 neutrons, so its mass number is 14 plus 20, or 34. And then ask what's the element? Well, we'll use the atomic number of 14 to tell us that it is silicon. I'll leave it to you as a challenge to repeat for calcium and selenium. But that finishes up section 4.